Hey everyone, how's everyone doing? Hope you're all doing well. Welcome. This will be part of a mini series where I'll be covering maths, chemistry, and physics topics and trying to basically condense them within short 5 to 10 minute videos for your leisure. In this video, we'll be going through chemical equilibrium, particularly rates of reaction, collision theory, and factors affecting reaction rate. So this topic can be broken down into two main umbrellas. Rates of reaction, which is what we learned in year 11, and in year 12 we'll be sort of building on top of that, and we'll be exploring product yield due to Le Chatelier's principle, or LCP, and we'll go into that a bit later on. So a bit of a recap in terms of reaction rates. So reaction rates, they're also known as RORs, are basically at some instance is the rate at which the reactants are used up, or at the rate at which the products are formed. Going back to sort of collision theory as well, collision theory basically dictates the what needs to happen for a successful collision, and it states three things need to happen, right? So the particles or molecules or ions must collide. The reacting particles have an appropriate collision orientation. So looking at the diagram below, a head-on collision is actually optimal and will yield in the highest chance of a successful collision or successful reaction. And the last thing is that the colliding particles must have enough activation energy for them to successfully react. So going through the factors affecting reaction rate, you've got 5 main factors, and they all can be pretty summed up nicely. So the first one being nature of reactants. So this is inherently the nature of the actual reaction itself. So for example, when you've got ionic reactions, they're quite rapid as they don't involve breaking of bonds or electron transfer between reacting particles. So ionic reactions are almost instantaneous as no reacting bonds have to break, and there is a strong electrostatic attraction between oppositely charged ions. However, for molecular reactions, for molecules, slow since they involve bond breaking and bond formation, and collisions are often unsuccessful at room temperature as they don't have enough activation energy. So ideally, molecular reactions are very slow. They're almost undetectable at room temperature as they involve the breaking of strong covalent bonds. So the second factor affecting reaction rate is the concentration or pressure of the reactants. So you can think of concentration and pressure as the same thing, as the same factor. However, concentration applies to reactants that are in the aqueous solution phase, and pressure for reactants that are in the gaseous phase, so your gas systems and whatnot. So going back to collision theory, because we always go back to collision theory, as you increase the number of particles per unit volume, this in turn increases the number of collisions and hence the number of successful collisions. So it becomes a bit of like a probability game. So you want to basically set up your reactants with enough, as much activation energy as possible, or basically orient them in a way that basically increases the chances of them colliding and hence the number of successful collisions. So for gases, I don't know if you guys know, but there is an inverse relationship between volume and pressure. So if you look at the diagram below, let's say you have a finite amount of space in a box, right? And as you decrease the volume, so you make the space smaller and smaller, you're basically effectively condensing all the gas particles together, making them bunch up a lot closer, hence increasing the pressure. So effectively, that's what's happening here. So when you bunch everything close together, pressure increases, and hence you're basically forcing those collisions to happen. The more high number of collisions, the higher proportion of successful collisions. Third one is called the state of subdivision. It's just a fancy word of saying surface area of reactants. So going back to collision theory again, the greater the surface area of the reactant, the larger the area for reactants to collide, and therefore increases the frequency of collisions, right? So for example, imagine you're making some tea. You got 2 different types of sugars, right? You got the sugar cube versus the fine sugar grain, right? So the sugar cube is represented on the left, basically just a cube, total surface area of 24 centimeters squared. Then you've got the exact same thing. However, you've now diced it up into 8 smaller cubes, right? Having a larger surface area. Because of the higher surface area, the fine-grained sugar will actually dissolve faster than the tea, and that's what the area of subdivision of reactants is talking about. Fourth thing we have is temperature. So kinetic theory states that as you increase temperature, so does the velocity of the reacting particles. That kind of goes back to kinetic energy. EK is equal to half mv squared, but this actually has a twofold effect on the reaction rate, right? So 1, the number of collisions per unit time increases, increasing the number of collisions and hence reaction rate. Once again, if you're increasing the number of collisions, you're increasing the probability of more successful collisions to happen, and hence the reaction rate. 2, the force and likely success of each collision increases. The proportion of particles with sufficient activation energy increases with temperature, and hence reaction rate increases. Once again, you're sort of so through increasing temperature, you're basically increasing the average activation energy for each reactant in that reaction. Going a bit deeper, so you can also have a look at the kinetic energy distribution and temperature. This is also represented by the Boltzmann distribution graph. You see this all the time in textbooks, and I feel like teachers don't do a very good job of explaining it, but I'll do my best to explain this, right? So ideally in this diagram, you've basically got two curves, right? One curve represents T1, which is at a lower temperature, and you've got curve 2, which is at a higher temperature relative to T1. And basically that point there where it says EA is the activation energy threshold, right? So anything below that, to the left of it, the particles and the reactants don't have enough activation energy to successfully react. Anything above it, at that point and above it, they will have enough activation energy to successfully react and collide, successfully react. So at T1, you see a smaller portion. So that shaded area under the curve represents the proportion of reactants that have sufficient activation energy to successfully react. And then if you look at T2, that curve sort of like pushed over, smoothed a bit. And if you have a look at the proportion, the shaded area, it's actually a lot greater now. So now there's a larger amount of reactants that have sufficient activation energy to react, right? So that's what actually happens with the proportion or percentage of particles with sufficient activation energy as you increase temperature. Last but not least, you've got the presence of a catalyst, right? So catalysts are these sort of cool things that you put in, but it's not consumed in the reaction. But it helps increase the reaction rate, right? A couple of examples you have, like real life examples, is basically H2O2 fuel cell. So think of a rocket, that's basically its fuel cell. If you add platinum, that can act as a catalyst to basically increase the reaction rate. And then you've got the Haber process, which is actually one of 2 industrial processes that you'll actually be going through later on in this course. The Haber process is basically the production of ammonia, right? So iron is actually the catalyst for this specific reaction and helps speed up the rate of reaction. Last one is vanadium pentoxide in the contact process. The contact process is basically the second industrial process that we'll be also going into, and it's basically the production of sulfuric acid. As you can see, this is actually the contact process is actually a multi-step process. It doesn't actually show the production of sulfuric acid itself, but it's actually I believe it's the second reaction in that multi-step process. So you need sulfur to create sulfuric acid later on. So, and the mechanism of how a catalyst works, it provides an alternate and lower reaction pathway with a lower activation energy. So if you have a quick look at the diagram below, the blue graph basically represents the reaction without a catalyst, right? So you start off as reactants. This is called an enthalpy graph. I don't know if you guys have gone through it before, but basically reactants, and then over time becomes products, right? But however, for the reactants to become a product, it requires sufficient activation energy to overcome that sort of hill, right? And that activation energy is given by that blue graph. So from the reactant to the top of that hill, right? Which is a lot of energy, right? The moment you add a catalyst, the pathway changes and you get an alternate one with a lower activation energy. So that's represented by the red graph. So now see how that activation energy is a lot lower. So instead of needing that much activation energy to successfully react, you only need this much now. So that means a higher proportion of reactants will have that sufficient activation energy to actually successfully react. So that's exactly what is happening there. And that pretty much sums up this video. I hope you guys found that useful. And once again, if you want access to the notes, just in the bio below. Cheers.